Hello everybody, this is Parker editing the the audio right now, and I am so sorry, but the beginning of the podcast, and I'm not sure, but probably all throughout, there are like these little noises of us hitting the mic, and it's kind of annoying, but there's like actually nothing I can do, so yeah, little disclaimer, but also we have a song that my brother made. His Instagram is DJ with the camera, at DJ with the camera. He made an intro song for the podcast. So I will let you guys listen to the podcast, and here's this cool song that we have now. It's the language of the universe.
I don't understand it.
Hello everybody, and welcome back to the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray, and we welcome you to episode 28, where today we have Matt Cater once again back on our podcast.
Except this time it is live. We are in person in the same room.
Unfortunately, though, we could not find a suitable camera setup, so we could not record this video. But hopefully we will be able to figure out a recording soon. But as of right now, here we are. So, Matt, how are you?
I'm good. I'm very glad to have you guys here. Awesome. By the way, we're live at my house, which is cool. Parker's in from Ottawa this weekend, and Ray's up in Richmond Hill, so they just came down. I'm downtown. I'm near campus and whatnot, so. Yeah, it was a good spot. I'm glad to have you guys here. And damn, it's my third appearance.
Yeah, that's awesome. Technically fourth because of part two.
Oh yeah,
because of part two.
Yeah, I guess technically
technically fourth.
I'm setting so many records on this show.
This is crazy.
This is so cool.
And also, we just hit a record of downloads in a day, and the day's not even over.
The day's not even over yet.
We got 160 downloads in a day so far.
That's actually really impressive.
Awesome.
It's got 6 more hours.
No. The day technically
ends at 8.
8 p.m.
It ends at 8 p.m.
It's a really weird day.
Yeah, because I'm pretty sure they're in...
GMT.
California
GMT. No, it's GMT. Oh. It's GMT. It works for GMT. That's why it's 8 p.m.
Okay.
Yeah, because that's 12 a.m. GMT.
Anyways.
All right.
Yeah.
For the topic of the podcast... we got a comment. Was it on Instagram?
Yeah, so we actually spoke about this in the previous podcast that real time we recorded today, this morning, actually. But we spoke about it, and I said that we're going to be talking about a few questions that people had, and one question that we got on Instagram was if we could give a few tips for pre-calculus students in college right now.
Yeah, so we're going to start off with that,
that's
and
what
then...
we're going to do.
Later on, if we have time, we're also going to talk about quantum mechanics and the quantum mechanics courses here at U of T.
Yeah.
Because Ray and I are taking 256, which is the second year version, and then Matt is taking 356, which is obviously the third year version.
Yes, sir.
It's going to be very exciting. Very exciting. Okay, so to start off, calculus tips, pre-calc tips.
So... I think we should start with algebra.
We'll start with algebra.
Just the most basic. I mean, technically it's like pre-calc.
Yeah, it's not really. Yeah, that's more accurate.
I think something that's really important about algebra is just being able to visualize functions based on just seeing the equations themselves. Like when you see, like it should be very natural to you when you see a quadratic equation. You know, like which way it's pointing.
Yeah.
You can take a guess at if it intersects the x-axis. Usually, if you have like x squared plus 5, it's not going to have any roots, things like that.
Right.
What about you guys?
That makes sense. Yeah, I mean, I personally think Algebra 1, Algebra 2 really important, and functions is not really... Functions, would that be... That's not algebra, is it? Isn't it?
It's not calculus. So
it's not calculus, but it's not algebra.
I guess.
Is function algebra?
It absolutely depends on how
how
rigorous you want to be here. Like if we're talking algebra in its real sense, then technically the algebra you're going to see in high school or in college, depending on when you do it, would consist of vectors in like a Euclidean sense as of right now.
Vectors.
Yeah, that is
we
algebra
really
or linear algebra.
Okay.
So that's
linear algebra.
Yeah, that's what we'll call it in the first 2 years, and then eventually you're going to generalize those algebraic structures to groups and rings and fields and all that fun stuff. But it's all in that world of vector space structure and other things. So that is technically, when we say algebra, we mean that. But to what you're going to know the algebra as right now, it's going to mean pushing polynomials around. So that's why we mean like functions.
So
and
basically just what you learn in high school before calculus. We're just going to
we don't
talk
mean
about
algebra and like a university.
It does get more specific once you actually go to university.
In university, linear algebra, I personally think I've mentioned this before. It was one of my favorite courses.
Yeah.
It's great with math. It's so interesting.
It works so well. I feel like the progression from like day one all the way to the end, where you end with eigenvectors and eigenspaces, it works seamlessly.
I just remember day one when I'm like, yo, this course, I can do it. Like, because I knew it, because it's basically revision, right? And I didn't know that at the time, obviously. Right. So like, I'm going through the course, I'm like, oh, I was doing well on the quizzes, the midterms. Yeah. And then like the second midterm hits, and I'm like, yo, it's kind of like all new stuff. I've never seen this before. Yeah. But like all the new stuff was still really interesting.
Of course.
You know, like that's the cool thing about algebra. Linear algebra.
A few things I'd offer in terms of pre-calc, prep, especially I'm assuming the viewer I guess I'm talking to now, and everyone, if you're going on to study a bit more math in university, whether that be for the purpose of physics, whether that be for the purpose of math itself, whether that be for stats, whatever it is. If you're in pre-calc right now and you want to really lay a foundation that's going to help you moving forward, it would just be familiarity. Just do and do and do. I know I'm talking soft skills here because we're not going to get into like nuts and bolts super specifically. Obviously, we don't have a whiteboard here again. But, you know, it's like what Parker said, like being able to visualize graphs of functions, given just kind of looking at them in terms of their equations. You know, your trigonometry is really important. It's one of the first times in trig identity is one of the first times you see, I'm going to loosely say the word proof here. Yeah. Because that's kind of, it's a proof in the analysis sense of the word, which for right now, for viewers, analysis is just going to be synonymous with calculus. That's just how we're going to say that, at least for now, for the pre-calc people, guys and gals. So, yeah, I mean, it's just familiarity. Just keep, I can't express how important it is for you to have those foundations laid, because once you kind of continue on, they're just expected to be very fluently laid in. That's true. So
that's true. No, but I think unfortunately, by saying this, actually one comment on one of our YouTube videos was, I was so lost during this entire podcast, but good podcast. I mean, it was still a compliment, but he was basic. And one person, which was actually quite sad, one person commented, I'm going into high school and this scared me for high school.
Oh no.
So that's, unfortunately we did that to that student, but that's not the point. The point is obviously to excite you. But like, I think when Matt says like to get rigorous about it, like in the beginning, the foundation is really important. Yeah. But as you continue it, like it'll just become natural to just do it.
Absolutely.
You know, it's not really going to become a hassle. Like right now you might think, oh, it's like an effort. I got to do all these functions. But like by the time you're in university, you're going to be steaming through them. No problem at all. So I remember it's just advancing in like your knowledge.
Yeah, I remember learning quadratic equations in high school. And like, obviously the very first question my teacher asked me was x squared, okay? Guess the graph. Oh. And I was like, okay, well, because I wasn't thinking in terms of like visual graphs. I was just thinking, okay, well, a number, you square it, it just gets a lot bigger than it was before. And then so, you know, I was drawing points on the graph and I'm like, oh wait, it's always like positive or zero. Right. But it's always positive. So it's like symmetric in the middle and it curves upwards. And that really built my intuition for kind of guessing, quote unquote, what functions look like. And I think that's really important as well. It's not only just doing the calculations and drawing the graphs, but really kind of understanding what's going on instead of just powering through
and like figuring it out yourself. I think that's really important. I think that's a big tip where like if a teacher, like if you have a question, I think a lot of times, like especially with problem sets, like problem sets are so good if you think about like in the long run.
Yeah.
Because they're questions that you cannot find the answer to online. Literally.
That's the whole point.
Cannot.
Or,
and you have to figure it out yourself.
Not only that, but there are also questions you can't answer off the bat. Like you,
exactly.
You have to think about
figure it out. And that, I think, is the best way of, I think problem sets are like the best way of applying your knowledge. Because like you can't search it up, so the only thing to do is to figure it out yourself.
And also talk to people.
Talking to people, socializing with your math groups, obviously, and understanding more. I think figuring it out, understanding it yourself is a very big tip.
Another thing I just want to re-emphasize what Parker said about the intuition and kind of getting what your teacher's putting down on a conceptual level. So I tutor a lot. You guys know that. And a lot of the students I tutor are grade 9s and up to grade 12. And I did a university student last summer. She was doing some pre-calc herself, actually. But one of the main trends I notice that people struggle with, at least my 2T did when she was in pre-calc, was the notions that were already introduced to her before that she didn't actually get on the deepest level. I know that sounds a bit general, so let me make it a bit more concrete. When I work with these grade 9s, it's the first time they're introduced to the y equals mx plus b. Everyone's favorite thing when everyone says, "Oh, I was so bad at math, lol, y equals mx plus b," whatever, right? Or linear relations and stuff like that. You know, and when I sit down with her, I always try my best to emphasize what we're doing here is not just plugging something into the formula y equals mx plus b. What you're looking at is what it's literally called, a linear relationship. You have a relationship between x and y, and the graph happens to look like a line, so we call that relationship linear. What we're looking at here is a function, and there's the relationship between its input, x, and its outputs, y. And that's what we call x and y because this is like 2D real space or whatever, but, you know, I try and remove her as much as I can from the specific and try to go abstract with it so she understands that, you know, our university accepted definition of a function, a rule that assigns blah, 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 blah. I try to hammer that home in, and early. And because, at least in Ontario, I don't know where you guys are listening from, we're obviously all here in Toronto, Ontario, they only introduce the word function in grade 11 as the academic course name. Before then, you actually never use, or they never use the word function. I don't know if it's intentionally not to ward off students, but I always tell my students personally, when they don't use that word in class, I introduce it to them, and then I'll say in the middle of the tutoring session, like tongue-in-cheek, hey, I'm going to use this phrase now. I want you guys to get used to it. So when we say, it'll say solve for, at what time does the ball reach this height, right? So that's saying, okay, insert the height as the output, work backwards, solve for t, in whatever the function may look like. But I'll say that. I'll say the question assigns us an output and we're looking for the input that mapped to it. And I'll make them get used to that because once you start hearing it, it's how your brain starts to say it.
Right.
You know, so that's what I think Parker was trying to get on. That's why I want to emphasize it further. Get yourself acquainted early. I definitely didn't, but I do that now.
I don't think any of us did because I mean we didn't really know what proofs was gonna be like or any of this.
I think one problem is that when people think about graphs, they think about graphs as kind of like a drawing on a 2D plane. They say this is what the graph looks like. But you're not supposed to think about what the graph looks like. You're supposed to think about how, like, don't think about the graph itself. Think about the x-axis and think about how the function warps the x-axis into place, right? It takes each input.
I like that.
And it takes each input, and depending on where you are on the line, it'll warp the axis to a different spot, right? Depending on the rules of what the function is doing.
Assignment.
And I think that's really
cool. So just to recap, yes, you're going to see a whole bunch of different stuff. You're going to see your trigonometry. You're going to see intro to polynomials. If they do it, I don't know if they do it here. They do it in calculus and vectors. You might see some matrices, which will solve linear systems for you. You might see some vectors. Whatever it is you see, really try and peel back, see the words they're omitting intentionally, and add them to your vocabulary.
Yeah, Mathew, be careful when you hit it because it spikes the audio.
Okay, well, we can cut this. We can cut this. But yeah, like I was saying, just reiterate that.
Okay.
That. Always peel back. Always take the opportunities to look a little bit deeper and acquaint yourself earlier rather than later.
I think the word function is pretty good to use on a young, like, to be honest, before I learned functions in school, like I'd learned functions before, but like if I was going just by the school, I would have loved to just know the relationship between these two things. And the word function, I think, explains itself a lot. Like if you say that, oh, y is a function of x, you're like, what does that mean? But you're like, hey, take time and distance and speed, for example. You can give it in like a real life form, so that
application,
and an application, so that so many people can understand.
Couldn't agree more.
Yeah.
Exactly.
Also, one thing, I don't know how to really word this correctly, but I think it's important to know that math shouldn't be scary.
Oh, that's true. A lot of people find it scary.
Yeah, that's
sad.
They see these symbols and they kind of, instead of looking at what the symbols mean, they just look at the whole picture and they're like, this is hard.
Just
like I'm just like afraid of what is going on
to
my
be honest,
on
I
my
kind of get
screen.
excited sometimes. Like sometimes I see some crazy integrals. I think I saw the first problem set that we had to do, and I saw a few things. I'm like, oh, I'm very excited to do this. You know, like that. Like if you have that reaction, you are like a math and physics student. If you see something complicated and you get excited, like that's it right there. That's your gut telling you.
Also,
it's sorry. Sorry. No, continue.
One thing I also wanted to say is that for people that are in high school and they say, oh, like this podcast is scaring me because everyone around me says they hate math, or there's the few that are like super good at math, so they but the thing about university is that you find more people that like math.
Yes.
Or I mean, in your field, right? Like that's the thing.
You automatically surround yourself with more people that are excited to do the work and excited to learn more, and that just puts you in the right environment to jam 100%. Things into your head.
Because in high school, I think a lot of times you can think of yourself as like, not an outcast, that's the wrong word to think of, but like as different, like, I like math, everyone's like just like, oh, math sucks, like that kind of vibe, and you're like, oh, I kind of want to be with the majority of the people, because everyone hates it. Why do I love it? Kind of thing. But it's fine, because the moment you come to university, you find hundreds and thousands of people.
A whole lot of people.
Not hundreds of thousands, hundreds and thousands. Hundreds and thousands of people that are interested in the same field that you are, and in this case, math and physics.
Yes.
And I'm not gonna lie, I did not know people like Parker. I've never met a Parker before in my high school, and then I came here second day of university. I met him, and it was and right then and there we just started talking physics. So just things like that you will find in university, you should get excited, not scared about. Is what the point I'm trying to push.
Yeah. So I mean, we can wrap it up on the pre-calc there.
Yeah.
But just to summarize again. It's just all about getting to the root of what you're learning and truly learning it, okay? And once again, it may seem a little bit daunting initially. It may seem a bit, like Ray said, different. You might feel like, oh, you know what? This is starting to get hard, and it's already different. So that's 2 strikes. I'm out. Like let's just make it that. Because I was only doing it because I liked it, but now that it's hard and different, then why am I even doing this anymore? But you may get deterred. It's because it's a new language. I mean, everything else is in a language that you've seen before, and
and everybody
gets... That's actually a really good point. I actually never thought of it that way.
Yeah, everything else is in a language you're familiar with. This is the only opportunity.
That's a really good point.
Yeah,
because math is like a whole new language in itself.
Yeah, we're gonna throw in CS in there, by the way. Also, I mean that has its own language too.
Yeah,
but but we'll throw CS under our physics and math blanket right now. Yeah. And then chemistry has its own thing going too, but
it's kind of related though.
Yeah, it's related.
I mean, physics and chemistry. Yeah.
We'll put STEM in our feeling different world.
Yeah,
I
feeling
air
different
quotes
world.
on our
STEM. STEM is good.
Sure.
STEM is good.
Yeah.
Sorry.
I forgot what I was going to say.
Okay.
It's okay.
I hope that helped. It was more like a soft skill thing. But hard skills are developed between you, your desk lamp, and your pencil and your paper. So what we're giving you here is the soft skills, which hopefully, you can develop them as well, but the hard skills aren't, developed here.
Yeah, I was going to say that it does get hard, but that's just part of it, right?
Yeah.
And everybody that studies math and physics has been there. Obviously,
everyone's been there.
You stare at a problem, you say, I am gonna fail this question because I don't know what to do. It makes you feel stupid, and it makes you feel like you have learned absolutely nothing. But I think those are the moments that you realize that, one, you are learning something that is much bigger and way vaster than you can ever comprehend. Yeah. And what you're doing is you're just trying to filter information into your head that is understandable, and that will increase your field of view into the world of math and physics, if that's your cup of tea.
Yes. And
it's easy to get discouraged, but it's also easy to change your point of view and change your attitude towards it, and say that, this is hard, but it's okay. And I'm going to learn, and I'm going to not necessarily try harder, because I don't think anybody comes to university and decides like not to try hard. Like you're trying hard from the beginning, but if you keep that sustained throughout, it's gonna flow easier or better into
And I think the best part about those questions on like the whiteboard or on the piece of paper that we're trying to solve, just can't solve. I think this is the best part about physics and math, when you finally solve it and you finally figure it out. You're like, hey, wait, we missed this, or like, hey, I saw this, or hey, I think I thought of that. The moment, like, you get that moment, and the satisfaction, or at least at U of T, I think this is how you prove things. Like you draw that box, right? Yeah. Like I think I've mentioned this before.
That's
that
not
box.
just U of T.
Yeah, that's not.
That's not. That's
everywhere.
Yeah. So that box, I think, is the most satisfying thing to draw.
Especially when you know your proof is wrong.
Okay,
the funniest.
Those are a little funny, not satisfying.
You know it's absolutely wrong, but you say, you know what? Box at the end.
QED. I know guys who put QED at the end of their exam.
I did that.
So funny.
I did that at the end of one of my questions.
Oh, I thought I killed an exam once. The extra piece of paper at the end where it's like leave blank, but I signed one. I literally just signed it. I thought I was like, I killed that. Didn't do as good as I thought. It wasn't like I didn't have a horrible performance, but I thought I like aced it. I was feeling cocky enough.
That's the worst.
Oh my!
I signed it. It was hilarious.
Oh my!
It was hilarious. I love that I did that because I can laugh about it now.
Yeah.
I feel like so confident exiting that exam room or whatever.
Terrible.
Get my mark back. I was like, damn. Okay.
Yeah, that was me on second midterm of 1 through 7. I walked out of there feeling so hot. I was like, man, last question. Killed it. Last question.
I wasn't even present for this midterm.
No, yes, you were.
No, I wasn't.
The second midterm.
Oh, the second
yes,
midterm.
Yes, you were there. We were proving limits.
Yeah, it's like
I didn't even do that bad on that midterm. No, wait.
No, second midterm you did bad. We all did bad.
Oh, yeah. First midterm is the one that you walked out all cocky and you did well, and I wasn't there for that.
First midterm?
You got the 80 on that one, and I wasn't there.
Right.
Second year.
No.
Anyways.
Second semester.
First semester, second midterm.
I was there for that.
You were there for that.
I was there for that.
And we thought we did well, and we almost failed it.
Oh, yeah. That's what you mean. I thought you were saying the other way around, that you did well.
No.
Anyways.
Yes. Sorry. A little complication there. Okay, so we are taking Quantum Mechanics 256, or Physics 256, which is Quantum Mechanics in the second year. And Matt here is taking Physics 356, which is third year Quantum Mechanics.
Yeah.
Now, we're not going to be specializing this, just the University of Toronto. We're just going to generalize third year versus second, so it can be applicable to most people.
Yep.
Right? So we haven't actually started 256, so as Matt, who's kind of been through it, how about it? What's the difference?
Sure. So I think we touched on this a little bit in previous conversations we had, but we can go a little bit maybe more in depth here. So 256 is something that the department does so that you've seen these ideas before they are formalized come 356. So it's not a material dense course per se, air quotes on per se. It's more of like a crash course in breaking a classical idea of physics that you already have. So, I mean, other people, I'm going to group under classical electrodynamics, or what our university deems electricity and magnetism. So those are still essentially classical ideas. No, they're not classical mechanics, but it's classical electrodynamics. So when I say classical, I mean including E&M. So back to what I was saying. the whole goal of it is kind of to introduce some experiments and talk about some things that went down in the last century or so that broke that idea for the majority of the scientific and physical community, that is, physics community, and then tell you why they broke down and then helpfully break it down for you as well. Because the type of approach to quantum physics is very different than the approach you're going to take to any other form of classical physics. Once again, another thing I want to throw in classical physics is the thermodynamics. That is another thing those are still considered classical ideas. Okay, so in 256, what you're actually going to see is the failures of classical physics. They're going to talk about the quantum revolution, which is a historical context, like I mentioned just recently, what happened in the last century or so, because all this physics is quite recent. You're going to look at the Stern-Gerlach experiment / effect, which is one of the main effects or experiments that kind of, triggered and had a big part in this quantum revolution. And then on the nuts and bolts, the nitty gritty of, you got to start doing some math at some point. You're going to look at the time-independent Schrödinger equation, which is the quantum analog to Newton's second law. So in classical mechanics, I don't know if you guys taken 254 or not yet. I think maybe you are right now.
Next semester.
That's for listeners, that's classical mechanics 1, not foundational physics 1, but classical mechanics 1. So that's the second year specialist classical mechanics.
Yeah, so
in that is the intro to those classical ideas and whatnot. But, like I was saying, in the quantum world, or pardon me, what I was saying is in there you use F equals ma everywhere. Of course, you phrase it in terms of differential equations and stuff like that. But the analog that you're going to use in 256 is going to be Schrödinger's equation. So that is the kind of the link there. And then within that, you're going to solve it as a PDE, as it is, partial differential equation for listeners. And you'll play with it a little bit. It won't be too crazy in terms of the math or anything, because a lot of the mathematical language of quantum mechanics is a little bit too advanced to go into for an intro course. But yeah, you're gonna look at some specific potential energy functions and then investigate what solutions the Schrödinger equation yields based on those. So I think you investigate the infinite square well, the delta Dirac potential or potential well, whatever you want to call it, and then the step potential.
We've already seen all
We've
three of
seen
those.
them, but we haven't really got
first year
deep into them.
Yeah, it was more or less like
just very.
Like, here's the infinite well. These are like you can have a sine wave, and you can also have higher energy levels.
We got psi here, psi there.
Yeah, and we didn't really like go into it like that, because it was also like last unit of the year. We had a month to go through it.
It's also technically an enrichment. It's not even like course material for 152. I assume that's where you saw it a little bit. Yeah. You'll also hear words like uncertainty principle. That's like what the YouTube gods love to talk about. Like you will see it formally, but you won't derive it formally. Like you'll use it, you will verify it. You'll take a physical scenario, a quantum scenario that is, compute those expectation values. So that means for all of you who have seen those videos, that sigma p / sigma x, that being the momentum in position, and you'll verify that inequality, the Heisenberg uncertainty principles inequality, holds. So you'll play with it a little bit. Like you'll see that it works. Like of course, you'll do a bit of interference packets, scattering and tunneling, and that'll all occur in one dimension. So, I mean, it's not the most clear course that I've ever taken. It could have just been my offering of it was pretty rough, to be honest. But I think it's just due to the fact that quantum physics is what it is. It's very different. Yeah. Just from all physical ideas I had seen before it. But yeah, any questions? Because I can just compare it.
I got a quick question, actually. Yeah. Do you need to take, or not need, I know you don't need, but should you take 256 before taking 356, or do you think it's not?
Okay, so...
or you think it's okay?
So 356's technical, requirements, in terms of physics, I'm going to assume you have the relevant math, which is a good year of first-year calculus or analysis, and a semester or two of linear algebra underneath your belt. Let's just say one semester, okay? U of T's prerequisite for 356 is 256
Oh.
or Chem 222, Chem 223.
Really?
Or Chem 225. So the reason why the Chem ones are an alternative is because they also look at microscopic structures of like atoms and things like that. So
we need to do 256 for 356.
I mean,
or the chemistry ones.
Yeah, the chemistry ones will. I can't speak for them. I mean, I didn't take them, but I think it's just because they also offer those foundational ideas, i.e., uncertainty principle, i.e., the true state of an atom is more of a probability cloud. It's not well-defined orbits. You know, they'll go into those sort of things, I assume. I mean, for the very limited chemistry I've taken. Would I recommend 256 over both of them? Yes. You're going to do more math. You're going to look through a true physics lens. So I think the reason they give that alternative is for chemistry students who want to enrich a little bit more on like the physics side of what they're really doing the chemistry with.
Isn't the third year quantum mechanics like a lot harder though?
It depends.
I mean, relative.
Technically, I've only been in it for a short bit now, but I looked at the material. Of course, I have the course text and whatnot. Spoken to some people in upper years. You're going to cover more information. Your mathematical maturity and knowledge base will be larger than it was going into 256, and that's important. Because the whole point of 356 is to formalize a lot of the ideas you got to play with and hear the names of in 256, i.e. buzzwords, uncertainty principle, statistical interpretation, wave function, Schrodinger's equation,
double
slit experiment, all those things. But really what 356 does is takes the mathematics of it and then makes it, just deepens it so you really know what's going on. I.e. in 256, you're going to say wave function, but you're not going to talk about specifically what it is as a mathematical object / abstraction. In 356, you're going to identify it as a member of an infinite dimensional vector space, Hilbert space, blah, blah, blah. Also fun words you may have heard on the JRE at some point. Okay? You'll go into general structure of wave mechanics. You guys have probably also already heard the term like energy eigenstates, eigenfunctions, eigenvalues.
Yeah.
Because the natural language of quantum mechanics is linear algebra and complex analysis / variables / calculus. So, I mean, that's kind of what 356 is going to do. 256 is there so that when 356 shows up, it's not, oh my god, on the conceptual level and oh my god, on the mathematical level. Because quantum has way deeper maths than the classical mechanics you will have seen up to it. Not to say like just deeper maths than classical physics as a whole. I'm never going to make that crazy generalization. But up until that point, the maths will have been nowhere near as deep as the maths that this physical theory is languaged in. So, I mean, yeah, it's more material dense and it's more math dense. So to an average physicist, they're going to label that as more difficult, right? I study math primarily, and then I do a bit of physics outside of it. So I kind of look at it as a beautiful application / use of things that I consider my field, if that makes more sense. So I felt more natural going towards it than 354, which is the third year advanced classical mechanics, right? I had the option between both for viewers. My program allows me to choose one, and I ended up choosing this one simply because I thought the math was really cool, and I just kind of had a good feel for it. So yeah, to answer the question holistically, you're going to get introduced to these ideas. It's going to feel weird. It's going to feel like pull and tug. And then in 356, you're going to formalize them. You're going to get the maths in there, and you're going to use the big boy words, big girl words, to be honest. Yeah.
How did you find the problem sets in 256?
I mean, we only had like 2 or 3.
Oh, really?
It was a horribly... Our instructor was very disorganized. So the problem sets were... I mean, it was a little weird. I mean, the first one would be very easy, and then the second one would have 2 questions that were really easy, and the third one would just be, I've never seen this before in my entire life, like Fourier transforms, and like, what is going on here?
Yeah.
For viewers, that's a mathematical like field / Fourier analysis. Is just well beyond the prerequisite for a second year intro quantum mechanics thing. It's like an advanced real analysis topic. But anyways, he did it very, very weirdly. I don't know which textbook you guys are using. We used Griffiths.
No, we're using McIntyre.
okay, I can't speak for McIntyre, but Griffiths was fair problems. And it's kind of fun because you use a different side of math that maybe you hadn't in a little bit or don't really use in classical physics again. So, I mean, the problem sets are fun in that sense, but they're also painfully confusing because we didn't have that much guidance. But also, that's just quantum mechanics. It's going to be confusing. It's going to be weird.
Have you, have you done Physics 224? Sorry, this is just a small tangent. Yeah. So, for viewers, that's the experimental physics for second year. And this is actually a pretty cool course because there's also a lot of computer programming with it. Right? A lot. So how did you find it fun?
It was a blast. It was also a headache. It was also like it was a long semester.
Oh,
it was a long semester.
Okay, you know what?
I mean, the requirements minimum are 6 hours a week in class.
Yeah.
So 2 lab sessions, 3 hours.
Because it's 3 hours twice a week.
That doesn't.
It's like physics. Practicals.
No, that was 3 hours a week.
Yeah, this is 2
Wasn't
sessions.
It twice?
It was once a week.
Oh, that was once a week. That's true.
Yeah, foundational physics first year would only require 3 hours a week. Practical physics or
6
experimental in second year is 6 hour minimum in lab time, and then a week, and then outside of that, you know, however long it takes you to write your report and do your analysis. That's the thing. You're only really gathering data during those 6 hours. So that doesn't account for your 12 hours of interpretation, analysis, review, conclusions, writing the code. You know, a lot of the code is far more advanced than what you had seen in like the coding you did in 151, for example.
Yeah, I'm excited for that.
I mean, they don't require computer science prerequisites because the TAs are there to walk you through the code.
Yeah.
And it's basically like a hold your hand through the code thing. But there's so much of it, and the TA obviously can't write the entire code for you. So the first 2 weeks are actually just a Python crash course.
Yeah, I know. You told me about that. I'm actually pretty excited for that.
Yeah.
I actually really enjoy programming.
Yeah.
I wanted the programming in math. Mm-hmm. That's why I tried to take statistics too with programming. Yeah. But unfortunately, I didn't get that because of the waitlist problem.
Oh, okay.
Yeah, so I'm actually really excited for the computer part of this
you're
lab.
Gonna do a lot.
It's gonna be fun. It's gonna be fun.
And it'll be like very pull your hair out at certain moments because you're gonna be like, I don't know how to do this at all. I don't know why. I don't know how to plot this like weird distribution or like, you know, perform these complicated regressions or these like whatevers.
There's some weird things.
I mean, it's a fun time, to say the least. You have your lab partner. It's you and him.
I don't actually think we have lab partners this time because
of
COVID, so it kind of sucks. So like there was one chair per table out of like 20 tables. I'm not lying. There were 5-6 people.
That's so unfortunate.
Like 6 people showed up.
Oh man! Before they were like, it was like a gym. It was just you guys just grinding.
Oh my!
After like their computers.
That's a good analogy.
Going at it, and the TAs were running around just like, no, do it like this and don't do that.
Yeah.
Oh my god,
I used to actually love my computer science classes because of that. Because it was basically all of us were on our computers just coding, especially during close to submitting the final project. Oh, I still remember that. We were all just code teachers just like running around. Like he's like, yeah, what's up? What do you want? And we're just all sitting there coding, and it's just crazy.
Just everyone. I think like the buzzword of that course was uncertainty. Everyone just was, how do you want me to do uncertainty propagation?
First project, uncertainty.
Uncertainty. That's going to be like the bane of my existence, that word. Jesus, that was so bad. They would, because I mean, it's important, especially for those who want to be, loosely speaking, practicing physicists. I mean, if you want to be a good scientist, period, you know, you need to get these lab skills in. But for those who are there for the credit, I mean, Jesus, the uncertainties were
too many.
So rough.
Too many
computationally dense, and the formulas were weird. And
we actually did a podcast on error analysis.
Yeah.
If you want to check that
out. Oh, there you go.
Yeah.
Yeah, okay. Yeah. You guys,
Yeah, it's pretty cool.
Yeah, so
I never found it fascinating. I always found it so
annoying,
so necessary.
Necessary for sure.
Painfully annoying. And I'll see like textbooks that are like so thick and just be like all about error propagation. I'm like, how?
No, but I mean, I guess error is though very. I mean, we
nothing works without it. Like nothing works.
Error is very important.
Yeah, thank God for people who care about it.
Yeah.
Thank God for doctors. I mean, I can't slice open people. It's just not anything I can do. So thank God for them. But the same goes for the guys who do the error propagation on like building a building.
Yeah, that's true.
I should have built my house. Like, it's just not something I ever want.
Nah.
That's
more like engineering type.
Yeah, but they still would use it.
They're going to use what the physicists and mathematicians derived. I mean, that's the engineer. He's a handyman. But,
we do all the brain work.
All the engineers out there.
Yeah. They're fuming. We love you.
Thanks for building stuff, I guess.
Thank you.
Thanks for actually getting things done.
We're just sitting in a room trying to think of things.
That's so true.
Yeah. And then, once per century, we'll be like, damn, this is kind of...
That's a good one. You guys could probably revolutionize the world with this or something.
Yeah.
Take it's yours.
Awesome. So yeah, we're actually at 40 minutes right now.
Oh, that's interesting. I'm okay, so... Small proposition what's happening as we're continuing to record more episodes is that Parker and I were talking about it this morning. We're just naturally moving to more time.
Yeah.
Like, I don't think we can cut it to 30 anymore. So we might move it to 45 minutes per episode.
Yeah.
And for all the viewers, the day is now going to be changing to Friday instead of Saturday. I mean, not that it matters, but I'm just letting you guys know if you do keep track and you guys are watching it, because I do know that some people have told me that I'm keeping track with all of your episodes.
That's fantastic.
Yeah. So for those of you that are, just telling you that it's now going to be on Friday at 10 a.m.
We had someone post on their story. They said like, I just caught up every single episode. So they just watched it, binged it. And
that's insane.
Awesome.
That is so fantastic.
Yeah. That's
shout out those guys.
I know, seriously.
Yes, we love everyone that loves our podcast.
Yep.
Everyone that tunes in, listens. Even if you don't love the podcast, but you like it, we still love you.
Yeah, I mean, we still love you. I mean, thank you for tuning in. That's all that matters. Thank you.
Yeah, and just to add to that,
and enjoying it.
I say this every time I'm on this podcast. I'm gonna say it again. It's so important what you guys are doing. Bringing all this stuff. No, oh my God, this is the word of 2020, and I can't believe I'm about to use it. Normalize. We're normalizing physics and math.
Hopefully, I mean that's the goal. That's the goal, right?
I'm so sorry, viewers. I can't believe I just had
that's
to do
the
that.
Goal. Because as of right now, I mean, it's kind of right that people are just like math, and we were talking about this throughout the entire one. That it's just so scary, and people are scared about it. Like it needs to be.
It's not scary. People need to understand. The reason why the theme of the podcast is space is because it's literally what we're studying. We're studying symbols on a page. We're not actually going to space and looking at stars. We're just looking at symbols on a page and simulations on a screen. But what it really represents is the entire universe,
so much
from macro to micro
quantum,
to look at your hand right now. The electron that is floating around in one of those atoms is, you have no idea where it is.
Air quotes floating around.
Air quotes floating around everywhere right now.
Give the physicists another century and be able to know what actually.
Exactly.
Who knows? Electron's a wave. It's a particle. It's everything.
It's everything.
Who knows?
It's everything.
Also, technically, there's a chance that electron is over there.
Yeah.
Technically.
Oh my God.
There's a chance that it's everywhere.
I'm saying it's non-zero.
All right, guys. I already have a quantum problem set, so I can't talk about this anymore. I'm getting enough hours a day.
All I gotta say is it's non-zero.
Okay? Non-zero probability.
But yeah, once again, just
pretty cool.
Super cool, super important what these guys are doing, what you guys are doing. And even cooler, it just shows, hitting the record today. I think it's so cool. I get to be on.
That's
awesome.
awesome.
You hit the record.
That's awesome.
It just shows that, people tune in. People are into this stuff, and whether it be taboo or not, I mean, it's important, and it's just human to be fascinated. And we're talking about some of the most. I mean, maybe we're not on this one. We're having fun.
Yeah.
But I mean, talking about some of the most fascinating stuff available to knowledge.
Yeah, literally.
So
literally.
The download show, we're normalizing.
Yeah.
I hate that word. We're normalizing, though. We're bringing it there. I'm not going to say weird.
Well, you are an integral part to this show at this point.
I mean, at this point, being on 4 episodes,
you're on more than 10% of our episodes.
That's true. That is
more
true.
Than
what can 10%.
I say?
That is
what
true.
Can I
that
say?
is true.
I think it's also fitting that that's the case, though, because so much of, what people, if you just take the everyday / average viewer who wants to kind of get into this is or is fascinated by it, this is what conversations usually kind of look like. Or
physics conversations. When you talk about physics with your friends, this is basically what they look like.
Yeah, and if you're stimulated by that type of conversation, or you get curiosity when you hear words you haven't heard before, like orbital angular momentum, fun, but whatever is, just you're like, ooh, what's that? Then,
spin.
When I heard of quasar, I was super interested.
I mean, I definitely didn't have things like this when I was just getting into it. I mean, I was watching PBS Space Time and
PBS Space Time. I love that guy. He has such a big head.
He's fantastic.
It's so interesting.
If I had never seen my peers though do, or people of my age group do anything but a physics contest or something, it just speaks to our generation's use of social media and how we communicate things and the excitement and everything. It's cool to see these generations, our generations, be so into it, and not just make it a astute practice or something.
It literally used to be a group of geniuses with top hats that would gather in Switzerland once a year.
Yeah.
And then just because they were extremely intelligent, they were the only people, right? The room was filled with geniuses and they were the only people that understood it.
Yeah. They also discriminated against a bunch of people who could have participated for sure.
That's true.
I do want to acknowledge that.
That's true.
That's true. But basically that's what it was.
But that's been the narrative. It's been presented in the last century, these topics, where it's this kind of exclusive club of, I don't, it's just all comes back to the I'm bad at math, air quotes. Math's not my thing, air quotes.
No one is, I don't really think anyone is bad at math.
And people use math every day.
You use math every day of your life. You're not bad at it, you just don't want to understand it. If you don't want to, if you don't want to, that's, I guess it's okay. But if, let's say, you're interested by it and you're scared so you don't want to, that's stupid. I don't think that's smart. If you're interested by it, and even if it looks scary and might be daunting, I still think you should definitely pour some more effort and interest into it.
It's a blast.
Because that effort will make that scary equation look exciting, look interesting, right? Because then you'll understand it. Once you understand it, you can solve it.
I think a big deterrent also is, you show up to class and there's always that one asshole that thinks he knows everything.
Oh, we had this in my class.
There's always that one guy who, obviously he's super smart, but it's just,
he's well versed. He's just a practiced kid,
He always raises his hand and he makes you feel stupid because he knows everything in the course. And, it's just, I think people like that should be a little bit more humble.
Yeah,
and
for sure.
Instead of trying to look like the number one in their class, they should help people
help the number 50,
smarter. Instead of just saying, you guys are dumb, I'm smart. Here's the answer. That's just not helpful.
I see so much of that spirit that you guys share in the creation of this podcast, period. You're trying to talk about these things in layman's terms and approachable terms and vibe-withable in air quotes terms. It's trying to take this scariness out of it and literally remove that guy's character, that quote unquote guy's kind of everything that he represents. Because it's not obviously just him. It's the education system, all these things that. And the media, the way media views and presents it, it's so cool because so much of the spirit you just expressed is literally almost a part of the purpose of podcasts like these. So it's super cool that these guys interact and they want to hear what we have to say. It shows that there's more like yourselves, more people who share that,
and that's good
kind of spirit.
That's exactly what we're trying to. We're trying to get. we don't have an ultimate goal, I guess. We're just trying to do it. Yeah. But, I guess it would be nice if we could get more and more people, understanding that it's not that hard. We're not trying to get you into math and physics. We're trying to get you to... Okay, no.
We don't have an ad campaign.
Yeah, exactly. No, that's what I'm trying to say. We don't have an ad, like, we're not trying to get you in. We're not like a cult. We're just trying to say that it's understandable, it's simple, it's interesting if you allow it to be. Yeah. That's what we're trying to say.
It's not even that you allow it to be interesting. I think it's just, like, we're presenting concepts that are explainable.
Yeah.
And you might think to yourself, like, a black hole. Like, what does that even mean? Like, you've never seen a black hole in your life, and you never will, okay?
I mean, pictures.
Okay.
That one image.
Okay,
two images are incredible.
You've never seen them with the naked eye.
Yeah, you probably,
But here's the thing. The human race figured out that they exist somewhere, and it's explainable and really interesting.
Yeah, so, it's actually really interesting. I think we spoke about this in the general relativity, or I might have in a segue or something.
Yeah, but another thing is that I want to say is I was actually thinking about it. I was either thinking about it or I was having a conversation with my friend about it, who was kind of asking about, just education in general, like what I studied, what he studies, and whatnot, and it goes beyond just this is interesting. Hope you like it. It's one of the rare fields where you're very literally developing a superpower.
Yeah.
If you are incredibly mathematically capable, you can go apply that to so many things and very literally save lives. I know people don't really think about that when they say, I'm studying math, what are you doing? When they hear a doctor, they'll think saving lives or something like that. Yeah. But this COVID stuff is a perfect example. When you have a worldwide issue like this, and you have things that are affecting people on such grand scales that, of course, governments are being involved. What people need to understand is there are mathematicians working around the clock. There are economists working around the clock. There are physicists and engineers working around the clock to mitigate effects of things like this. Whether that be keeping federal debt in check, whether that be allocating resources correctly, modeling infectious disease outbreaks. People are working 18 hours a day, mathematicians, to make sure that society is as good as it possibly can be. If they model correctly or they, can predict effectively, then they are very literally getting resources where they need to and hence saving lives if they can get them there in time. So when you can develop these skills, once again, physics being another one of these skills where you can apply it to engineering and do anything, you can do so many big things. You're developing your superpower. It's really an incredible thing. And then you can go apply it wherever you want. And that's what's so great about things like this. It's another reason why I love tutoring. I love doing things like this, sharing, is because if you can equip a next generation or other people with those superpowers, they can go use it too, and they can go make differences and not just, use it to, apply it to some hedge fund, make a whole bunch of money. I don't, that's the joke within our community, sell your soul to finance or whatever. But you can go work in a financial institution, raise a bunch of money or, restructure some sort of pricing model or something and end up helping a non-for-profit that needs that money somewhere else. There's so many things that go with math other than just what you're learning right now and in pre-calc or wherever you're at listening to this. You're getting the superpowers. You're practicing your sutures for the surgery analogy. You're practicing your scalpel technique. It's like cutting butter. You're I'm not saving lives yet. Yeah. You're no, you're not yet. But you're developing these skills. Yeah. It's what they can be applied to, Yeah.
And because it's so, it's not elementary anymore.
No.
You can go so far into math and physics nowadays that you have to be in training for a very long time before you actually do anything.
You can't just
you can't just be thrown into the front lines and then expect anything to come of it. You need to do the work and train yourself before you can actually step out onto the field.
That's why I wanted to give these examples, because I want people to understand that these areas do not exist solely in academia. When people think mathematician, they think physicist, they think white dude, nice big beard, he's a professor, whatever it is. But if you walk into Public Health Canada in certain offices or the CDC, you're going to find mathematicians all over the halls there. Like I said, working around the clock. Walk into a financial institution, you're going to find economists who are mathematicians. They probably have a master's and undergrad in math and then did economics in their postgraduate studies or something. You're going to find mathematicians everywhere and physicists everywhere who are, not just this academia-based thing. They're all over the place. They work for every business. They work, So it's important to start thinking of these professions in those lights so that people can gravitate more towards them,
That's right.
as opposed to just the genius with the round glasses and the button up and the khakis or whatever it is. That is one job in the field.
Yeah.
The applications
there's so many more applications of physics and math
to
than
just
people
becoming
realize.
a professor.
Yeah. Like, people are like, oh, I'm going to get a PhD and become a prophet. I mean, no.
You probably won't.
I mean, first of all, there's a big percentage of physicists that do go into finance and computer science and
that's
government
another one.
and stuff
Computer
like that.
science, beautiful example.
Computer science, I think, is a very usable, very, very useful application.
It's literally
of both
responsible
math and
for
physics.
how we live our lives every single day.
Exactly.
I mean, to keep the banks going, to keep everything. And that's another one for computer scientists.
The stock market.
And
relies on
also
software.
the reason you're hearing our voices right now.
Exactly. Like, all of this is computer science, which is engulfed with the reasoning of physics, which is engulfed with the calculations of mathematics.
Yeah. I mean,
so it all ties together.
Mathematicians, physicists, computer scientists, they're everyday people too. But, the same way you can start viewing doctors as everyday people. But, it's more than just a niche hobby / practice / area of interest. It is truly universal, and there's so many more professions, careers, and just endeavors and passions and routes you can go down in these fields that are not just academia. So I feel like a lot of people aren't turned on to that. When I had that conversation with my friend, he was like, "Oh, I never even thought about that. That there's mathematicians in Public Health Canada right now making sure we're okay." Or there's do you know what I'm saying?
Yeah.
They don't think about biostatisticians who are at the CDC right now, working in teams with these mathematicians, applying their biological knowledge of the disease and their immunological knowledge of all these things, and then working with the mathematicians on a day in, day out basis to build these models to make sure everyone's okay, to allocate resources, all these things, So let's try and take a little bit of what we understand of the word mathematician off and look a little deeper, because they're everywhere.
Yeah.
A mathematician is not just
a prof. Or,
for sure.
Or like a guy sitting in a research institute.
Yes,
not
absolutely.
only the 2 jobs.
Absolutely.
you can do.
Yeah.
Yeah, so we're coming up on an hour.
Yeah, we're definitely... Okay, so...
I wanted to add that thought for sure.
I think the 45 minutes was a lie. So we're going to continue, hopefully, the next ones for 45 minutes. Because I think that's seemed like a natural transition.
I don't think it matters, to be honest.
Yeah, I mean, it doesn't really matter. I mean, it could be just however long it is,
Correct.
it doesn't matter.
So we are going to cut it off here.
Yep.
Thank you for listening to this extra long episode. I hope you found what we were saying to be captivating or maybe even interesting.
Yep.
So, I'm glad to see you here at the end of the podcast. Thank you for listening. Make sure to follow everything. You know what I'm about to say. So, this has been episode 28 of the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray, and we will see you soon.
Thanks for having me, guys.
No problem. See ya.